Alright, now this is a supplementary video to the class. And I explain what spin-spin splitting is. As we talked about in class, if I have a carbon with a hydrogen right here, and it's next to a carbon that has 3 hydrogens nearby, we know that this particular one is going to be split by its 3 neighbors using the n+1 rule. The number of neighbors this hydrogen has is 3, so we have 3 plus 1, and this is going to be a quartet. And since all 3 of these hydrogens are equivalent, those 3 hydrogens are all going to act as the same signal. So this hydrogen is the only neighbor to these 3 hydrogens, so my neighbor quantity is 1 plus 1. And 1 plus 1 is a doublet. Now you'll want to ask yourself a question as to why we have something that's a quartet and something that is a singlet, or excuse me, a doublet. So with the doublet, let's examine that first. Okay? Since we all have the same signal, they're going to be coupled by something that's nearby. Something that has 2 different spin orientations is going to give 2 different coupling patterns that we'll be able to detect in the NMR. Okay? So with this particular signal, since it's being split by this particular neighboring hydrogen, this guy over here, there are 2 orientations that this hydrogen can have. It can have an orientation of the spin going up, or it can have an orientation of the spin going down. Since there's only 2 particular spin orientations that can split this thing, each one of these particular signals is going to give to a different signal. So that's why we have the doublet, one represented by an up signal and one represented by a down signal. Okay? Now when we go to the more complicated form, this particular quartet, I'm going to make a little bit more space here. The quartet means that there are now 3 particular signals which can give different types of spin coupling Hertz constants. The first one is if all 3 hydrogens, and that's these 3 hydrogens up here, 1, 2, and 3, if all 3 of these hydrogens, so I'll call them hydrogen 1, hydrogen 2, and hydrogen 3, if all of them are spinning in the same direction, okay? So all 3 of them can spin in that particular direction, okay? That means that we've got a magnitude that is basically multiplied by all 3 of them pointing in the same direction. I'm also going to have a setup where I've got H1, H2, and H3, where I'm going to have 1 pointing down and 2 pointing up, or I could have this one, number 1 pointing up, number 2 pointing down, number 3 pointing up, or I could have number 1 pointing up, number 2 pointing up, and number 3 pointing down. Notice that the magnitude of each one of these spins is going to be the same because each one only has 1 down arrow pointing down. Okay? So as we do a mathematical function to figure out the magnitude of those, each one of these is going to be an equivalent signal. Since there's 3 possible signals here, we're going to see 3 times the size of this signal on the NMR spectrum. If I see this and go in the down direction, I see something very similar to the one we just looked at, with 1 down, 1 up, and another down, or 1 up and 2 down. And down here I've got 2 down and 1 up. All of those are also going to have the same magnitude. Since there are 3 possible spin coupling forms of this, we're going to see a magnitude which is 3 times greater than our first coupling, which only had 1 possible combination to give us this particular coupling. And if you can now guess, you know that you have H1, H2, and H3. If they're all pointing downwards, then I'm going to see a particular spin coupling which is going to look like that. All right. So for this, essentially, what a quartet boils down to is something that's got a 1 to 3 to 3 to 1 ratio, simply due to the fact that there's 4 different ways for spin coupling to affect this and cause the splitting on the NMR spectrum. And that's how we figure out proton coupling in a proton spectrum.